Hello. Yeah, am I audible?
Yes, Rajesh, we can hear you.
Yeah, thanks. Yeah, is my screen visible to you?
Yeah, we can see it.
Yeah, thanks. Yeah. So in this chapter, in this section, we will be seeing logistic regression and defining the cost function for them and how to make binary classification as well as multinomial classification. Those kind of sections we will be seeing today. We will be discussing those things. Yeah, we will be learning along those steps. Yeah. So logistic regression, it's used for classification problem, but in the name it looks like regression is there. Regression means predicting something in the continuous range of variables, sorry, values. But in classification we will be classifying it as assigning some categories. So the word itself coined in such a way that it is used for classification, but the term logistic regression term will have something called for regression. So why it is like? So we will see that the math behind it a little bit. Yeah. So the logistic regression, in the normal linear regression we will be framing some mathematical equation that best represents our input data. In the same way, along with that input data, sorry, along with the modeled one, we will be applying a function sigma over it. The sigma is this function is called sigmoid function, and this function what it does is it will squeeze our range of values into in the range -1 to +1. So in this way we can make our model to work for adaptive for classification problems. So this is one way. So it will make adaptive for the classification problems. So if it is a binary classification, then we in the linear regression. So this part is still linear regression. We will be applying the sigmoid function over the sigmoid function is also known as logistic function. That's why the name comes like logistic regression. We are applying the logic function over the result of the regression. So what this does, it will this logic function, it will just squeeze the inputs, squeeze the values that it is getting into the range -1 to +1, and it will cut. It will crosses the value 0 at the point 0.5. So if we see them, visualize them, it will be like this. So this is the curve for that exponential. So it is in the range x is equal to in the range -7 to +1. It is perfectly, it looks linear. The slope will vary accordingly. And if we consider it goes after this point, it goes like asymptote to the one. It never touches because it is an asymptote. In the negative end, we can see as t approaches negative infinity, we can say that it approaches -1. It's another asymptote. Yeah. It grows towards touching 0, but it won't touch. So it will squeeze the input in the range 0 to 1. Here we can see that after point 2, so it will be going to 0, and in this top end it will be going towards 1 and not beyond that. Yeah, that's why they put a dotted in the line. Here we can find that some dotted one. So this represents some important region. It's like it's growing in a asymptote. Yeah. Here we are visualizing as if there is only one variable. So in our case, we will be having some equations. For example, this is just one such example. It may not be in the real time. We may be getting different coefficient, different set of variables. So this will be the corresponding hyperplane that's getting learned by the model. And this is the contour plot of the same. And this is one more, one such, one some other example. Sorry, not this one. Sorry,
Hey,
please ignore
Rajesh,
this. Yeah, yes,
I had one question.
yes, sir.
Uh, like I got a little confused when you said about range -1 and 1, and the text
I'm
was
sorry.
saying
I'm sorry
something.
for saying it's a 0 to 1.
Okay, okay.
Yeah, it will squash sigmoid function will squash the ranges of values into 0 to 1.
Okay.
In the left extreme, it's 0, but it don't touch us. It's an asymptote. Yeah, in the as t approaches infinity, it reaches 1.
Okay.
Yeah, sorry for confusing. Yeah. Yeah. Then the next one is how do we define our cost function? In regression stuff, we will be doing since it's some continuous range of values, we will be finding the difference between the predicted versus the ground truth. Then we will do the mean square error of them. So likewise, since it is a classification problem, then how do we define the cost function? Yeah. And we know that the sigmoid will gives the range of values in 0 to 1, and it crosses uh, 0.5 at the threshold 0. When t is 0, it reaches 0.5. Right? So the 0 to 1. So this corresponds to something, we can make it as some probabilities. The probabilities ranges are values within the range 0 to 1. So we can take this as a probability range, and since we are seeing about binary classification as of now, if the value is lesser than the threshold 0.5, then we can make it as a class 0. If the value is greater than or equal to 0.5, then we can assign it to the class 1. So like that, we can just map the logistic regression outputs to binary classification. Okay, we have defined something. um, how can we model like that? We have defined. So in that, what is the cost function that we are yet to define? So in this, the cost function here we are going to see is this one. First let's see the curve begin log of x. So this is one curve for log of x. In this curve we can see when here this is for log x, when the x approaches positive infinity plus infinity. When x approaches positive infinity, it is going it is curving, it is growing like that. When it is approaching negative infinity, it is less than 0. It does not crosses 0, it is less than 0. Okay, but the curve we want is negation of log x. So yeah, so this is the curve that we need here. Yeah, here when here it is negation of log x when x approaches minus infinity. Then we will be yeah yeah there is the when x approaches our values, the probability values lies between 0 to 1. Yeah, so when x approaches towards 0, we will be having some positive values. The values are greater than 0. When x approaches 0, we will be having positive values. When the x approaches some positive values, some values greater than 0.5. In our case, we are considering threshold as 0.5 for time being. So when it is greater than some 0.5, the value is decreasing. Okay. Now we will relate this with the cost function defined here. We will have some actual class, and just assume the another one is a predicted class. Okay. If my actual class is 0 and my predicted class is also 0, then I don't need to penalize the model anything. Similarly, when the actual class is 1 and the predicted class is 1, I don't need to penalize the model. Okay. Suppose if my actual class is 0 and it is predicted as 1. So if it is predicted as 1, what does it mean? It means the value of the probability here is greater than 0.5. If something is being happen like that, then I have to penalize my model by something. To do that, so please keep in mind that if it is predicted as greater than 1, then the probability value will be greater than 0.5. It is wrong. It has been happened, but it is wrong. So yeah, so it has been wrong. Yeah, so the probability value is greater than 0.5. So the probability value will be greater than 0.5. So when the probability value is greater than 0.5, the curve, logarithmic curve, approaches 0. The function that we are focusing only within this range. Beyond this range, we don't have any, and log is not defined for the negative values. Yeah, but our range of concentration is only with the range 0 to 1. Yeah, when it is greater than 0.5, so the curve, the cost function, it is trying to make it as 0. It's like we are penalizing the model. Correct. So my actual class is 0 and predicted as 1. So if something occurs like that, um, what the threshold value is 0.5, but the cost function reaches 0. But we can't, if we do like that, if we assign the value 0, then the cost does not change anything. So we are, and since we are seeing it as 0 and 1, we can see it like this, predicted as not 0. Um, if we see like this, predicted as not 0, yeah, if we see like this, predicted as 0 and not 0, what is the probability that it is not 0 is greater than 0.5, and what is the probability that it is equal to 0? Then it will be 1 minus the predicted probability. So if we compute that score, then we can see that our cost is somewhat positive value. So accordingly we have defined here when the case. So that's why we are doing negation 1 minus the inverse probability like this. Okay. So let's see the other end. When we have our actual value, actual class is 1 and the predicted one is 0. In other words, not 1. We have to stick with either one, either 0 or either 1, and other one as not 0 or not 1, like that. We should not make any interchangeable. So let's stick with it. The class 1 and it is predicted as 0. So if it is predicted as 0, then what it corresponds, the score corresponds to What does it mean? Means the probability value is lesser than 0.5, but we don't want that because it is wrong, because we want the actual class is 1 and the predicted one is 0, and then the prediction is based on the cutoff some 0.5. So this values, and if something is predicted, then I have to increase the, if this situation occurs, then I have to increase the cost function. So the cost value will be increased here. Accordingly, it's like we are penalizing the model when wrong predictions has been happened. Then we will define, we have defined the cost function. What happened when we predict 1, what happened when we predict 0. Okay, then we are combining them and then writing it as a single equation as here. Okay, so in this the thing we are very much, we should be very clear about this is log t approaches 0, yeah, grows very large when t approaches 0. It's like if you have some plus infinity, the log t value will be very less. When the log t coming towards 0, the value is becoming very, very high. So we are able to see that in the curve here. Yeah, that's a thing. On the other hand, minus log t is close to 0 when t is close to 1. The region that we are focusing only on 0 to 1. In other regions we are not focusing, since our probability ranges lies within 0 to 1. Okay, so accordingly, this is our cost function in case of binary classification. Okay, and there is no closed form solution exists for this to minimize this value of theta. Yeah, and they are saying that it's the cost function is convex. Why it is convex? Because we are seeing the curve here, right, in the range 0 to 1. So it is there is only one global minimum exists. So visually we can find that there are no suboptimal minimum, some kind of stuffs here. Then we can make it as a plot here also. Yeah, we can make a plot here. Y into log p so this is something for y into log x plus 1 minus y into log of yeah, this is the equation that we are seeing here, y into log p plus 1 minus y into log 1 minus p, the same equation, and there is a minus in front. Yeah, and this is the curve that we are getting for this one, and here our y corresponds to some multiple this p corresponds to our sigmoid function that we have seen sometimes before. So like that it will be the cost function will be. Here you can see that at the range y equal to 0.5, we will be finding something that origin kind of stuff, some global minimum kind of stuff. It will be lying somewhere like that. Yeah. Then as usual, then the next step will be we will be doing that the gradient descent. So
excuse me. So Rajesh, in this equation, y is discrete. although P is a probability, is a continuous probability between 0 and 1, but Y can only be 0 or 1. So this 3D plot is pretty, but it's not really representing the situation, you know, in this particular case.
Mm-hmm. Yeah. Yes, Joseph. Yeah. As you said, the Y that we are seeing here, it is 0 to 1. But in our actual scenario, we will be getting either 0 or 1. Do you mean that, right?
Yes, in any two-way
Yes.
classification problem, you only have Y equals 0 or Y equals 1.
Okay. Yeah. Yes.
So what you could do is take a slice through the p-values for Y equals 0 and plot that, and then plot another slice through Y equals 1 and plot them, overlay them on the same plot. That would give an interesting plot. Do you see what I mean? If you take a slice through Y equals 0, parallel to the p-axis, and then take another slice through Y equals 1, also parallel to the p-axis, and look at those two curves.
So yeah, to just follow up on Joseph's point, yeah, so like in this equation here, for every instance, for example, now we're talking Y is either 0 or 1. So for every instance, we'll either be using the first part of the equation, that the Y times log of PI, that instance, either that or the other one. We will never have both of them at the same time being used. Think of it, for example, if Y is 1, right, then we'll be using the first term. And then second term is what it's going to go to all 0, because we're going to have 1 minus 1, so 0. And same thing. So if Y now is 0, we will be using the second part. So I just wanted to to clarify that. And I feel I mean, I'm just saying, because this is a very, very important equation. So I just want all of us to maybe to pause here and really ask any questions, if there are any questions here. This is what we also call the cross entropy, or the log loss, cross entropy. So if anybody have questions, please do ask questions here.
So Rajesh, if you wanted to, you could just set Y equals 0 in that equation and plot it, and then plot it again with Y equals 1, and then overlay those two plots. That would be interesting. Yeah. Oops. Let's see what happened. Oh, it's minus 1 log y minus p. Minus 1 log. What happened? P has to be between 0 and
0.
Yeah. Why is there a real part and an imaginary part? That's what I don't get. Y equals.
Y equal to 0.
Oh,
we are in this range. 0
you
to,
have to, yeah, you have to restrict the range. That's right. Just from 0 to 1. There we go. Yeah. So if, let's see, if Y is equal to 1, and we know we have a positive case, then if the predicted, let's see, if, let's see, that's P. So our loss function is high when the probability is near 1 for the case, for the positive case, and our loss function is low. Let's see, why? Seems like it should be the opposite. No, this is the case 0. This is the negative case, right? Yeah.
0.
This is the negative case, right? So we have a low loss function when our probability is near 0. That means we're doing well. And if our probability is near 1, then the loss function is high, meaning there's a penalty for guessing. There's a penalty for saying that we have a high probability of a positive case when the actual truth is that it's a negative case. Does that make sense? And if you plot the other way around, the positive case, you'll just get, I think you just get like a mirror image of that plot.
Yes. We'll be getting something like this.
Yeah, exactly. And that's the case when the truth is y equals 1. And so when you guess a probability of 0 for the y equals 1 case, you get a high loss. And when you guess a probability of 1 for the positive case, then you get a low loss at the right-hand side. Yeah.
Then
Joseph, shouldn't this curve be the other way around?
This is the first, the blue curve is for the negative case. In other words, you know,
y equal to 0.
Yeah. Does that make sense to you now? That this is for the case of y equals 0.
Rajesh, can you go back to the curve, please?
Yeah.
Okay, so here what we are saying is that this is the plot for the above equation, the -1 log 1 minus p. So
Yes.
this equation comes down when we have y is equal to 0. So that's why we are dealing with the negative case. So for the negative case, now if the probability is low, in that case the cost is low as well, because the prediction is also that it is negative case. So that's why the cost is low. And if the probability increases towards the end of 1, which is a predicted 1, in that case it is a wrong prediction. So that's why the cost function goes up.
Exactly.
Yeah, we can in other words, starting a point, we have to increase, we have to maximize the probability of predicting the class as 1 and class as not 1. If we say the probability of predicting the class as 1, as we have to maximize it when the actual ground truth is 1. We have to maximize this probability, maximize the probability. So accordingly, we have to penalize the cost function. So if the actual ground truth is 1, so that one we will see it in this plot, the plot that we are able to see.
Just for completeness, yeah, can you overlay the minus log p plot in red over that one? Minus log p, yeah.
Yeah.
Yeah, minus
you
log
mean
p.
Here itself?
Yeah, but make a new plot that overlays on the same figure.
Yeah, I think that one I'm not aware.
It won't let you do that?
Overlaying, I'm not aware.
I see. Well, then you could just make a new plot for the case of y equals 1. Just minus log p. Yeah. There we go. Yeah.
When y equal to 1, so our cost function reaches, so if we are predicting the actual value 0, sorry, actual value, so our actual class will be assumed that is 1 and our prediction is 1. So in this scenario, okay, we are perfect. We are perfect means we will be lying in this range, so the cost will be 0. And similarly, if our actual data is 0 and predicted as 1, then while doing the while computing the cost, then we will be getting some high cost here.
Yeah, we have to remember that the P is the P hat is the probability of class 1. That's what P hat means. So if P hat is 1, that means you're saying the probability of class 1 is 1. And that's why you're getting a perfect cost function at 0. But if your probability of, and then at the other end, when you say P hat equals 0, that means you're saying the probability of class 1 is 0, and then you're completely wrong, right? And so you got a really high cost function at the left-hand side. And if you're close, if you say the probability of class 1 is somewhere like 0.9, then that's good, you have a low cost function. But if you say the probability of having class 1 is 0.1, then you're back to, you have a wrong, you have a high cost function, if that makes sense.
So yeah, team, is there any queries in this section in understanding this one?
Now let me just write something here. I just wanted people to remember that P hat is defined as the probability of having class 1. Sorry, that's bad, but better than nothing. Right, that's what the P hat is. It's the probability of the positive class, right? And that's what we're plotting on here on this axis. And then this on the vertical axis, this is the cost function.
Yeah.
I have a question here. So this plot is the plot of cost function as we change P for y is equal to 0 and y is equal to 1 separately. But how do we know that the total cost function with respect to our parameters is also convex?
For this question, yeah, the question is, if we have y equal to 1, we will be using this. If we have y equal to 0, we will be using this. Then how come we know that we have to use this one or that one? Am I right, Gautam?
I just want to know, how are we sure that the final cost function with respect to our parameters is also convex?
Yeah, well, if you look at
this,
if you look at this function j of theta, that's the cost function summed over all the examples, and it's just a sum of functions that look like this plus functions that looks like this, right? And the sum of two convex functions is also convex, and so the sum of all of these things.
It's not a simple sum, right?
It's not a simple sum, but it's like a linear combination of. Actually, it is a simple sum because it's always, the y is always going to be 1, either 1 or 0, right? If it's 1, you select this term. If it's 0, if it's 1, you select this term. And if it's 0, if y equals 0, then, sorry, let me get this back. If y equals 1, you select this term. And if y equals 0, you select this term, right? And so you're always going to have either you're going to have a sum of a bunch of terms that look like this, log p of I. And the other side, so that's these terms, because the y is always going to be 1 for these terms, right? And on the other side, the second term, you're always going to have terms that look like log of 1 minus pi. So,
yeah, but
right?
At a particular example, it's either one or the other. You're not adding both.
That's right.
So
exactly. That's what I'm saying. Yeah. For each example, you get a contribution that's either this function or that function. That's what I'm trying to say, right? And so if you have a positive example, then you have a contribution this. And if you have a negative example, you have the contribution that looks like this. But we've seen that both of these functions, one of them looks like this, and the other one looks like sorry, I forget which is which. Yeah.
Sorry.
Yeah, one of them looks like this and one of them looks like that. So we're just adding together a bunch of terms that look like this or look like that. And the sum of convex functions is always convex. Does that make sense to you? Every example is either positive or negative, so it's going to contribute a term that looks like this or a term that looks like that. And when we get through summing them, we're just going to have a bunch of terms like this, a bunch of terms like that. You know, and there may not be equal numbers of those terms because the data set may not be balanced. But the point is that it's always a sum that looks like that, and therefore it's convex. Does that make sense to you, Gautam?
Not completely, to be
Okay.
honest.
Gautam, this Srinivas. So you have an excellent question, and I'll send you a link offline. Actually, I'll post it if others are interested. But there is a more recent paper from Google which talks about the fact that the convexity of, in this case, the logistic function with respect to the last layer doesn't imply the exact question you're asking, the convexity with respect to all other parameters, but it's still convex with respect to the last layer. And you can chase down the details from the blog and the paper that I'll post. But
what do you mean by last layer?
The last layer of the network or any function that you're using. I was talking about it with respect to a neural network, but with respect to, for example, this particular, in this case, it's just a function. So if you use the logistic function in a neural network and apply it to the last layer, then that's with reference to that particular layer or the parameters of that layer versus the parameters of the all of the layers or the entire function and the data.
Srinivas, can I ask a question on
Sure.
on just the methodology there? When, in your experience, when mathematicians and computer scientists come up with an idea that, okay, we're going to improve the optimization function, we're going to make that change to the very last layer. How is it? To me, it sounds so much like p-value hacking. You're trying lots of different things. What is the formal way in which they come up with that idea to test and make that valid mathematically? I'm not sure if my question was very clear.
No, actually, I mean, in fact, Joseph has a degree in math, so he can talk to it. I'm more an engineering person, so I apply math.
Open question. If anybody,
just some guess. You asked that our theta values, it will be optimized for something. So it is some local optima, and we are trimming the top layer and adding our custom layer, custom classes or something, whatever it is. Then after adding this, what will be we are optimizing the local minima further according to the problem. So somewhat it will be like that. As per my understanding, it is like that. Already we have some local optima identified model. We are starting that as with that as starting point. We will be seeking different local optima with the last layers removed.
So it seems, I guess I need to understand, this is Joseph, I need to understand your question a bit more, Mash. So when you do ImageNet, let's say, and then you simplify it to a dog cat classifier where, like Jeremy does that when ImageNet has 1,000 classes, and then Jeremy simplifies it to a dog cat classifier that has 37 classes, right? Something like that.
Exactly.
Right? And so you're not doing anything illegal. You're just saying, well, I have a classifier that works for 1,000 classes, and now I just need to chop that last layer off and replace it with a classifier that works for 37 classes. So it seems to me that you're not doing any p-hacking. You're just saying, this is the model I need for my classification problem.
Okay. I get that better now. Thank you. So
does that answer? I mean, I'm not sure what your actual, if there was something else that you.
It was Srinivas's point earlier that Google came up with a paper where they said, we're going to tweak that last layer. In this logistic function, this would be the logistic function itself is like the single layer, I presume. So these tweaks that we would make to say, all right, we're going to shift the sigmoid function ever so slightly this way.
Yes, and they're based on extensive mathematics, not all of which I can claim to understand, but they have to prove it in order to get it published. And the references I pointed to are actually, most of the paper is the mathematical proof of why they are doing it and why their choice of the actions they take makes the function more robust to certain conditions that that we are facing in real life compared to the ideal situation. So if you follow the paper, most of it is referring to the math behind it. And we'll get to a little bit more of the math in this discussion regarding cross entropy, as somebody mentioned as well.
So Srinivas, would you mind posting that on the Slack too?
Yes, I will.
Thank you. Thank you.
Thank you, Srinivas. Really appreciate it.
I would like to say something. So Joseph, to just follow up to your point. So you see when you mentioned when we have 1,000 classes in ImageNet, but we're only dealing with like dogs and cats, or maybe relating to the other question. So usually this is what we know as transfer learning. You see, like, so you can actually do transfer learning, and maybe you can do it on something different that has like 10 classes, right? And then you bring it to your application, and your application has, for example, 2 classes. And then that's kind of the same with ImageNet. So, and that's where you do, for example, either you remove the last layer, or because what are we really looking for? We're really looking for the weights all the way from the first layer towards the end. Not necessarily to even include, like, not even including the last layer. Yes, sometimes, you know, we can include it if it's the same number of classes, but usually if we just take off the last layers, that's still good enough that we can just, that's what we call fine-tune the model to our new few samples or smaller data sets, and for it to work with that. So yeah, so I just wanted to kind of like clarify that that's what's going on, you know. So like when for example Jeremy, he brings the ImageNet, yeah, he brings it, but then he says, you know, now I'm classifying for dogs and cats. That's kind of what you meant, Joseph, right?
Yeah, so initially he has a model whose last layer has to predict an integer between 0 and 1,000. But that's when you're doing ImageNet, because you have 1,000 different classes. But when you're classifying dogs and cats, you only have 37 classes. So now you want a model that will predict integers between 1 and 37. There are 37 different classes instead of 1,000 different classes. So instead of having the last layer being a softmax over 1,000 classes, the last layer becomes a softmax over 37 classes.
Exactly, yeah.
Thank you, everybody.
Yeah.
Really appreciate the digression.
Just one point I'd like to discuss here. So as we are talking about the convexity of the overall cost function for the logistic regression, so going into math is one way definitely, but if we think about it intuitively, can't we think it this way? Let's say I'm just annotating a little bit over here. So for this equation, this j theta equation, the one curve that we got is something like this. This is for one of the cases, I forgot for which one. One equation is like this, one plot is like this, and the second plot is like this. So now I understand that these two plots are for two different cases. Probably this is for y is equal to 0 maybe, and this is y equal to 1, and maybe vice versa. So my point is that now this equation, this overall equation that we are seeing here, it's a combination of both, right? So can't we think it this way, that this is the overall, like the overall plot for this j theta, this one is going to be just a sum between these two, which will be something like this, maybe something like this. which is just a vanilla addition between these two.
Well,
Like
it's not just the sum of those two. It's going to be the sum of a bunch of those curves, and each one of those curves might not exactly look the same because the probability distribution might be different, but it has the general shape of that first. The curves we're adding have the general shapes of those two curves that we drew, and we might have 100 samples, and 70 of them might have curves of the upper type, and the other 30 might have curves of the lower type. But the point is that no matter how many times you add functions of the upper type plus functions of the lower type, you're going to get a convex function, because you always have to get a convex function when you add together two convex functions.
So does this logic cater to the need that the explanation regarding why is it this whole thing is boiling down to be a convex function? Is this an acceptable logic that for whatever number of times we add these two things, but eventually these things are going to be addition of these two curves, which in any case of time is going to boil down to this kind of shape. So is that a fair explanation of why this is a convex function?
Yeah, in a sentence, it's the sum of convex functions is convex. That's all that's happening here, and the J of theta is a sum of convex functions.
It sounds like you're both saying the same thing to me.
Well, yeah, that's right. We're just saying it in different.
Sorry,
we're just saying. We're just sort of. Yeah.
Sorry, please come again, Brian. Something you said. I'm sorry, I missed it.
I was just confirming that it sounds like they were agreeing, and we can move on.
Okay. Yeah, this is for visualizing softmax. This is not. We are yet to see this. So just for visualization, the relevant topics I brought in. Yeah. So yeah, we have defined our cost function for the logistic regression. So this is this equation they coined them as log loss, and yeah. So here is the one. So we are since we are dealing with only one class. Actually, it is two class, and we are finding them as whether this is class one or whether this is not class one. So we can say that it is though the number of classes are two, we can say them as in one classifier we can make it. So this is as Joseph kind, it will be defined only for 0 or 1. The intermediate values won't be there. So then the corresponding gradient calculation values will be like this. And yeah, the next one, the key thing is the decision boundaries. Here there is a problem of classifying the flower as it based on its petal length and the sepal some attributes. The sepal is how large is this one. So this is one such flower, and for this flower how longer it is. So this is some sepal, and like that what is the length of this stem, something called the petal. So like that there are some features. So in this flower virginica, it is both of them are a bit higher. In setosa, the petal length seems to be smaller, but the sepal is very high. In versica, in versicolor, it's some inverse. Yeah, and if we make some classifier in logistic regression, we are identifying that whether it's iris virginica or not. Yeah, if that is a case, then what we will be doing is our model will be learning something like this, some logistic regression curve like this. Just for it will be defined only for the point at 0 and for 1. In other cases it won't be. Yeah. So here we said right in our previous case at the probability value of 0.5 we can decide it, but it is not the optimal always. So it depends on our data. We have to choose our threshold value. In some cases 0.5 works. In some cases it will be somewhere around 0.5. It's not exactly. When the petal width is greater than 1.5 centimeter, as per the probability 0.5 cutoff, we can say that it is a iris virginica flower. when the petal length is lesser than 0.5, we can say that it is not a iris virginica flower. But as per our data, we can find that these are the some iris virginica flowers having lesser petal width. So there is some cost involved here. So finding the optimal probability to decide which class it is, which class given flower is. So to do that, we need to study the decision boundary over some plots. So like that, this is one among them.
Rajesh,
Yeah, yes, sir.
I have a question. So the
Yeah, yes.
author said the petal width of Iris virginica flowers ranges from 1.4 to 2.5. But when we look at the chart, it's like starting from 1.8 where the two sigmoid curves intersect. Why does it then go as low as 1.4? Because
I'm
below,
sorry.
so do you get my question? Like in the sentence in that paragraph below the chart, he said the
Okay. Yeah.
the
The flowers
petal
ranges
width
from 1.4 to
1.4 to
2.5 centimeter.
2.5. Yeah, but if you look at the sigmoid curve, it's like where the two
Yeah.
sigmoid curves meet and where the probability is 0.5. It starts from 1.8. So I was a bit confused. Why did it go as low as 1.4?
Okay. Yeah. Here you can find that in the actual data. So this corresponds the region that we are seeing. It corresponds to Virginica flower, and this point corresponds to petal width of 1.4. That's why he mentioned it is 1.4 to 2.5 centimeter. Yeah. Does it clarifies you? I'm sorry.
No, because when you look at the decision boundary where the probability is 0.5, it actually starts from 1.8. And so we can
Correct.
say with all certainty that above 50% it's an Iris
Okay.
virginica flower. But why does it go as low as 1.4, which is below the
Let me
decision
add some.
boundary?
Yeah, if we see the same, the iris virginica flower ranges from 1.4 to 2.5. Similarly, some not iris virginica flower are in the range 1 to 1.678. We can see that. So there are some intersections are there. So some overlapping is there, but we are not confident that with what can be the optimal threshold value so that we can perfectly classify it. So that's like some definitely there will be a there will be something exists, always it exists like that.
The
And if
triangles.
we go with if for example if we make some cutoff here, we can damn sure tell that it is not virginica flower. If we make some cutoff here, we can say that it is pretty sure that it is iris virginica. But in this, within this region, there will be some cluster, some mixture of that. The plot for yeah, the plot for our sigma, we can tell that within some range it will be perfectly sloped, and in some places it will curve at the towards the end. So that reflection we are seeing here, it's like the decision making, the making decisions in the mixture of classes, it is like that. So what is the optimal decision that as per the business need we have to decide.
Okay, that makes sense.
Yeah, because in this problem, because this is predicting whether the flower is this category or another category, so it does not make much sense. In some cases we will be finding whether it's a tumor or not. So it depends on the business problem. So which area we want to tell confidently.
Shamsuddin, is the question is regarding why the decision boundary is at 1.6? Is that the question?
So the question was why did the author go as low as 1.4 to say that the petal width of the Iris virginica starts from that range? But when you look at the chart, the decision boundary starts at 1.8. But I get Rajesh's explanation now.
Yeah, yes, please.
So regarding this one, where the petal width for the Virginica ranges between 1.4 to 2.5, you can do one thing. You can plot out the data set that is there for all the data that is there for Iris Virginica. Then you can bring up a mean and max. That will give you the range that is there, actual range that is there in the data set.
So I think maybe this answers your question. The probability, the decision is made when the probability is 1/2, right? And that's why the decision boundary is 1.8, because that's the intersection. Both of these curves intersect at probability of 0.5, and so you'd make your decision. The decision boundary is when the probability is 0.5, and that corresponds to this decision boundary of 1.8. Does that answer your question?
No, actually,
Yes, it does.
the decision
Thanks.
boundary, it is at 1.6 actually. So the decision boundary,
Whatever.
why?
Yeah.
So why the decision boundary is 1.6? It is actually an output of the model. If you go through the notebook, you will understand. I can quickly share the. Can I quickly share the screen for a moment?
Yes, please.
Okay, thanks. So if you go through the notebook that is there associated with this chapter, you can see my screen, right?
Yeah, yes, yes.
So here you can see here what they are doing is that they are trying to, in order to come up with the decision boundary, first they have come up with a line space. So this is the line space between 0 to 3, which encompasses this whole range, 0 here and 3 here. After that, what they're doing is that on top of this one, this is the model that they have come up with previously. They have trained the model. So this is a trained model. With this trained model, they are predicting the probability on top of this line space. So they're coming with a range of probability for all the data that is there between 0 and 3. After that, what they're doing, this is the decision boundary they're calculating here. So how they're calculating that is that from this output, they are finding out all the data that is there for greater than 0.5, which signifies a positive class. From there, so another thing is that this is an ever increasing data space. So as it starts from 0, goes all the way to 3 with 1,000 intermediate slices. So this is basically an increasing or sort by ascending order. In that order, so the output also is going to be in that ascending order. So from here, what they're doing, firstly, this internal portion that I've highlighted, it is going to give us all the data for which it is class 1. From that data, they are pulling up the first one. So this is a sorted, basically. This is a sorted output. From the sorted output, they are taking out the first bit, and so that the rest of the item will always be to the right hand side of this one. And from there, they're coming with the decision boundary. So that is the reason the decision boundary is here, which if you find out here, if you print the decision boundary, it is giving something like 1.6. So this is the way they are coming up with the decision boundary.
Yeah, and it's exactly what I said. It's where the probability is 0.5. That's where you have the decision boundary.
Right, this one. Okay, so thanks.
Yeah, and it is not always optimal that 0.5 as the cutoff. So depends on the problem is that we have to change it slightly.
So for binary classification, isn't it always going to be 0.5 only?
No, it is not. It depends on the problem that we need.
Okay.
Our model will learn something, and this 0.5 is it's some generic cutoff. So our model might predict, for example, this is one such thing. Not this one. So if we feed some input data, then it will predict. Then over the period of time, we have to analyze what is the optimal threshold. So the cutoff range, everything that we have to make it find out.
So is it something manual that we do while going through the problem statement, or is there any mathematical way or programmatic way of finding out that one? I mean, optimizing that one.
As per myself, yeah, it's some plotting works, and apart mathematically, I'm not sure about that. I'm sorry. So plotting, we always do the plotting stuff.
So it is more like a visual representation. From there, get your decision boundary.
Yeah.
Mm-hmm.
Yeah, you just tune the threshold empirically. You just set it at different values and see which one gives you the best accuracy.
Okay. It's kind of a trial and error.
So here we comes the most of the queries will get answered here. Here we are seeing that this petal length and the petal width, and in this the line in the black, dark black, we can see that it is the cutoff corresponds to 0.5. Then another one is 0.75 and another one is 0.90. Similarly, in the below it is from 0.15 to 0.90. We have different cutoff plotted here. So in this plot we can find that when if we consider our cutoff as 0.15, then we can see this is some Virginica flower, and this is some Virginica flower. So we are guaranteed that whatever we are plotting as not Virginica, it is very confident, but we are not confident that it is Iris Virginica or not. So similarly, if we consider our threshold as 0.90, we will be confused in this range. The range that we below this, we will below this 0.90. If we consider above, it will be Iris Virginica. We are pretty sure about that. But if we consider this case, there are some cases we are misclassified. So the finding threshold needs some plot, kind of interactive plot, and then some decision making. Accordingly, we have to make decisions. So the cutoff that we make that decides which one we are going for, and it's purely based on the business problem. We have to make which side we are liable to make some misclassification.
Yeah, so when you choose the threshold, you can have whatever criterion you need for that problem. I mean, you could just have the threshold, the criterion that you want to maximize the accuracy. But if this is a problem where mistakes cost, other kinds of, like either misclassifying one or the other class causes a big problem, you can actually change the penalty imposed by different kinds of errors, and then come up with something that's tuned for your problem. Or you could just go by straight accuracy. There's a lot of ways you could do it.
So it is like thinking about whether what costs us more, whether it's false positive or false negative.
Yeah.
That thing we need to consider.
Yeah.
Mm-hmm.
Yeah. Next one is we can use as we did with the linear regression, we are adding the penalties. So L1 and L2 some regularization that we can add here also in this. So if we add them, we will be in our cost function. In our cost function, we will be having some extra stuff that will the theta square. We have to minimize summary weights of theta square if it is L2. If it is L1, we have to the modulus summary value of the theta. That one we have to add if we use. And here in this equation also we can find that it is J of theta. Please here theta is something is hidden in this P value. Yeah. Then the next one is Softmax regression. In the previous chapters, we might have seen that multi-class classification. It will be taken as one versus all and the one versus one approach. For example, if we have some 3 classes, then what we will do is class 1 versus class 2, class 1 versus class 3, then class 2 versus class 3, like that. 3 different models, or else there will be a one model, one for class 1 versus class 2, 3, 4. Similarly for class 2, another model, whether it is a class 2 or not. Similarly for class 3, we have another model. So if there are some n classes, we have some n models. So this is called one versus rest, and this is called one versus one and one versus rest. In one versus one, we will be finding whether it is class 1 or class 2, whether it is finding class 1 or class 3, whether it is class 2 or class 3. But in one versus rest, we will be finding whether it is class 1 or not class 1. So we will be finding like that. So let's stick with one versus rest now. We will be training some independent classifiers for some n number of classes, and then these classifiers will give us some predictions, and with that result we will be doing something. How we are mapping those results to solve the actual classes. So that's what we are going to see in the Softmax regression or multinomial regression, logistic regression. Yeah. So in that, what we will be getting is, this is for some class K. Yeah, the equation that we are seeing here is for some class K. It's not for all. So for our input features X, for example, some in our case is petal length, petal width, something. So something like that. Then for the class K, class K means, for example, if it is Virginica flower, we have some theta values. For another flower, we will have some other theta values. So like that, we have to compute individual theta, so individual parametric values. Then we have to do sigmoid on top of them. Sorry, softmax on top of them. The equation for softmax is exponential. It's like proportional exponentiation. At the end, we will be getting something like this. Yeah. Yeah, this is what we will be getting. So after doing that proportional, that softmax, we will be getting probabilities like this: p equal to 0.7, 0.2 for class, different classes. And if we add everything, it will be 1. Yeah. To find the maximum, what is the which is the correct class, then we have to find the index of the maximum probabilities, and then that one we can take. For in this case, we can take this the first one as the maximum one, so we can assign the corresponding label to the values. So this is softmax regression. Then the cost function correspondingly is this one. For different classes, we have to find this logic. We have to in the earlier case, in binary classification, we have seen that we are trying to maximize the correct class, and trying to minimize the other class. So 1 minus we are neglecting it, and then we are trying to maximize what is the correct class. That is what we are doing in the multi-class classification.
So if you think of softmax can be thought of as a generalization of the logistic function for multiple classes. It maps. It does the same thing that Rajesh Kumar told us that the logistic function does. It squishes inputs between 0, and the output is always between 0 and 1. The logistic function does that, and also the softmax function does that, as you can see. No matter what the input is, the output is going to be something between 0 and 1. And so it has all the properties of a probability, and that's what it's doing for you, just like the logistic is doing that for you in the single class case, or in the 2-class case, sorry.
Joseph, one trivial question. So in the logistic function, the sigmoid function basically also comes with the notation of a sigma, and the softmax function, they're also representing a sigma. So what is the difference between them?
Yeah, I think he doesn't need to do that. This is this equation. Let's see. Let's see. So I think you're referring to this thing here, right?
Right.
Yeah. So this is some unfortunate notation that he's introduced and not explained, but I think he's basically saying that this is a generalization of the sigmoid. This thing here is the generalization of the sigmoid for multiple classes. And if I were you, I wouldn't pay attention to it. I mean, the main thing to look at is this and this. This is giving you a probability for the case class. Yeah.
I have to have a doubt here. So if if some class K is there, if multiple classes are there, then if we apply the sigmoid function, if we simplify the equation, do we get something like this?
You know, I think the only way you get something like that is if you take the sigmoid applied to the class, the case of just two, you know, the two classes, 0 and 1. I think he's introducing some new notation here. This is kind of a generalized sigmoid function. So sigma, I mean, it's basically a different sigma. It's sigma sub k, and so it's basically, he's basically saying this is a generalization of the sigmoid function, but he's not really saying it in so many words, but that's what it implicitly is doing, right? It's mapping the score, which is this s of x, into a number. It basically maps this, so it's a mapping. It maps the score of x onto the interval 0, 1. So it's mapping the score into a probability, just like the sigmoid is. But this is doing it for a multiple class problem.
So what Rajesh is also saying, I thought about that one as well. So if we think about the sigmoid function, it is like 1 by 1 divided by 1 plus e to the power minus t. So that's for 2 plus problem. Now if we expand it if we expand this function, what it becomes is that e to the power t by 1 plus e to the power t. That is, if we simplify it, that is what it becomes. Now if we compare it to this equation, in that case it is approximately the same. The only difference is that in the sigmoid function there used to be a 1 in the denominator, which is missing there in this case, because if we see, the summation is from j is equal to 1 to k. So we are never going to have one term here. That's the only difference I could see.
No, it's the same. It's actually the same, because if you take e to the x over, let's see, if you take e to the x over 1 plus e to the x, that's the generalized. That's if you take this generalized thing and apply it to the 2-class problem, right, Subhashish?
Right.
And then
right.
if you reduce this by dividing numerator and denominator by e to the x, then you do come up with exactly the same equation. You get
Joseph, actually I was saying just the same thing, the other way around. So the original equation, if you see, they have said 1 by 1 plus e to the power minus t. If I simplify it, it becomes the left hand equation that you have written, right? E to the power x by 1 plus e to the power x. Now that is for the 2 plus problem. If we, as you were saying, I'm saying the same thing. So if we expand it from multi-class problem and we compare it with the equation 4.20, so in that case it things falls into place. The both of their numerator having e to the power something like x divided by again some summation. Now the only difference I could see is that in the numerator the e to the power x matches between the 2 class and multi-class. In the denominator also the e to the power x terms also matches. The only difference I could see is that the one term that you have written in the denominator, that is missing in the equation 4.20's denominator.
But it's not missing, because this is the equation you end up with the 2-class problem with this equation, right?
Right.
But what I'm saying is that this reduces to our familiar form of the logistic function if you divide the numerator and the denominator by e to the x.
Mm-hmm. So if we compare these two equations, so in the equation 4.20, how are you getting the one term that is there in the denominator?
Because there's a 0, okay, because there's e to the 0 plus e to the 1. Those are the two cases. E to the 0 when the score is 0 or when the score is 1.
But in the equation, that is the point, right? The 0th term is missing. The summation is from j is equal to 1 to k.
Yes, but in this case we have two classes, j equals 1 and j equals 2. And the j equals 1 corresponds to the 0 class, and the j equals 2 corresponds to the 1 class. That's how you would apply this equation to the 2-class problem. And so there is a 1 in the denominator.
Okay. So you were saying if we expand the equation 4.20, we are going to get a 1 in the denominator.
Yes, if you do it for k equals 2, for the case k equals 2, right?
Okay.
Yeah.
Okay, I understand. Okay, I'm getting your point. Okay.
And
yeah, thanks, Joseph. Yeah, it clarifies a lot.
hey, Joseph, when you said this is not the best, maybe representation for this, like the sigmoid followed by the score. Why is that again? I mean, because it seems, I mean, this looks correct to me, right? I mean, he gets the scores and then he applies the sigmoids to them. So, what is it that you're thinking isn't quite right there?
Because this is not the same sigmoid as the one he's defined before. This is a generalized sigmoid. This is a new notation. You know, it's sigmoid on something with a subscript k. So this is basically a generalized sigmoid for the case of k classes. And he doesn't really say, so he's introducing this implicit new notation, but he's not really saying what he's doing. That's my quibble with this. It's fine, really, but you know, he's not doing anything wrong, but he's just not explaining what he's doing.
Yeah, and also it confuses the usage of sigmoid and the usage of softmax.
Yes.
It conflates the two, which isn't helpful.
Yeah.
So basically, the sigma symbol stands for what? Is it for sigmoid or for softmax?
Sigmoid is what, the reason why they call it sigmoids is because it's an S-shaped function. So the sigmoid is just was defined for the two-class problem. And so this is really, you know, whenever you see, I mean, we data scientists, whenever we see sigma there, we're always trained to think of a simple sigmoid function. But here he's introducing this notation for the softmax function, and that's what's a little bit, I don't know, it's not incorrect, but it's just confusing things a bit.
And to follow that, so by the way, we're talking about logistic and sigmoid. You know, like, let's just keep in mind that sigmoid is just one special case of a logistic function. So, you know, like, because like a logistic function really encompasses many different functions. Like sigmoid is one of them. Like 10H is another one that is also like a logistic function. So I just want that you know, that to be clear. There is like a general logistic function that maybe if you Google, you'll find maybe it has like a growth rate, and yeah, maybe I'll Google that in a second. And from that, sigmoid is just one case, and yeah, so yeah, let's just keep that in mind.
Yeah. So yeah, as Joseph said, we have expanded. Yeah, when the number of classes equal to 2. For class 1, I'm just writing S1, S2, S2. So we will be getting, for the class 1, we will be getting exponential of S1 divided by exponential of S1 plus exponential of S2. And for the second class, we will be getting exponential of S2 divided by. So this is what we will be getting. So if we simplify them, then the terms, as Joseph said, we will be getting some, 1 in the denominator. Yeah.
Yes,
Does it clarify?
Yes, I understood that.
Yeah, thanks. Yeah. Then the next one is, yeah, this is the corresponding cost function and the corresponding gradient vector for this. So yeah. So when we're doing the multinomial, earlier we have seen the decision boundaries, and in this case we are having 3 classes. So we'll be having the 3 classifiers, and the 3 classifiers. For 3 classifiers for the iris virginica flower, we can see that the petal length versus petal, yeah. So there are, this is the line 1, this is the line 2, and this is the line 3. Different thresholds we are being getting, and so this is, so whatever threshold that is greater than 0.5 and the petal length greater than less than 2.5, we are sure that it is iris setosa. Similarly, if we consider the petal length greater than 3 and the threshold something lesser than this 0.90, then we were sure that it is very scalar. It is very scalar. If the petal length is greater than 3 and if the probability values are lesser than 0.9, then it will be most likely that Iris virginica, this flower. So our decision boundaries, we have to make find the decision boundaries which optimize, which has less penalty over our model. And this is one such visualization for k is equal to 2. That softmax that we are seeing. This is one such visualization in the three-dimensional way. Sorry. Yeah. So after that there are exercises, so we can wind up. We will recap this chapter now. Yeah, and one more important thing is in the logistic regression as well as in the Softmax regression, we will be using our model will throw out some probability values. With that probability values, based on the cutoff, we have to decide which class it is. So in the Softmax predict probability, we are finding that the 5,2 is for, one is for petal length and another one is for so petal width. So the two features they are passing in, and for that features we are getting three different probabilities. So this is one of such probability, and then after doing Softmax, which is the maximum that we can take. Yeah. So now we will recap this chapter. So this chapter is very core for most of the upcoming chapters, and there are some math involved. So that's it's okay to skip the math part. That's fine, but trying to get it's very good to getting to know that. Yeah, we have started with a linear regression and the closed form of the solution, normal equations. Then instead of the closed form solution, we will be doing something different way, that is called gradient descent. And how it works is by computing the gradient. Gradient is nothing but the rate of change of a function when we change something. If it is only one variable, we can see it as a slope of a line. We can visually see it. If we consider some multi-dimensional, then it will be something called gradient. Yeah. Then the next one we have seen is polynomial regression. So instead of having the linear, we will be adding some synthetic features to the linear regression. That the synthetic features is of higher degree of our existing features. Then we will make sure whether our model predicts good or not. Then accordingly we will decide which is the optimal number of, which is the best way to represent our data. Then the next one is our learning curves. We have been studied the effect of the size, training set size with the underfitting and the overfitting, and how can we decide, when can we say that our model is underfitting, when can we say that the model is overfitting. So those kind of such stuff we have seen here in the regularization. So what happens when you do the normal regression, there will be a chance that overfitting may occur. So how can we make the model not to overfit? So to adding some extra minimization terms, so that it is not getting into overfitting. So that it avoids overfitting. So those kind of steps we have seen in the regularized linear models. Then in logistic regression in today, we have seen how to make some binary classification and what is a cost function to define that, and the corresponding how to calculate the gradient for that. So mathematically we have not stepped in, but so we are getting familiar with those equations and how to find the decision boundaries. Based on the business problem we have to choose. And what if our classes are more than 2? So we have to use Softmax regression in those cases. So these are the cases that we have seen in the chapter 4. Yeah. So if you have any other queries or anything, can step in, jump in specifically, and then. Hello.
So, any insights on like how one goes about choosing that specific decision boundary? Like, what are the things one could consider? I mean, I understand that it can be very specific to the particular problem, but just wondering aloud.
Yeah, 0.5 will drive us. The cutoff threshold of 0.5, it will give us something. Then we have to make a trial with a 0.4. Then whether our F1 values, since this is the classification problem, we have to choose precision, then the F1 and those metrics, precision recall on the F1, those kind of metrics we have to go. Then we have to check for our F1, whether it is increases or not. If it is increases, then we have to step down to some other values, 0.42, then 0.3. If it does not, then we have to increase our threshold. So like how we have to proceed.
So this is essentially a hyperparameter then.
Yes, kind of that. Yeah.
Yeah. So for example, Anand, suppose that you're doing a two-class problem, right? And so there are two kinds of errors you can make. You can make a false positive detection, classifying something in the positive class when it's really a negative, or the missed detection where you classify something that really should be classified as the positive class into the negative class. So those two kinds of errors, your corporate bosses might decide that the false positive error costs them twice as much as a false negative error for that particular problem. And so they might tell you that, and then you could incorporate that into your modeling. You can introduce a penalty for false positives that's twice as high as the penalty for false negatives, and then you can so you can put that into your modeling, and then you can try different thresholds and get the one that optimizes that cost function, the one that penalizes the false positives twice as much. Does that make sense?
It does. Yeah. I mean, I actually am working on something like that. That's why I was interested in this, but more in a deep learning context. Just wondering how I would go about building that cost function, because I do have a case where I have if I have false negative, it has to be penalized higher than a false positive, and there are certain numbers to it, like a 2x versus 1x and such. So in like I'll put this on the Slack because I think it's a slightly tangential discussion than to what we have here.
No, that's very interesting. Yeah. But I mean, I think in general, you have to just devise your own metric. In other words, write a custom metric function, for evaluating the model. And in that evaluation function, you reflect that the cost of a false negative is twice as high as the cost of a false positive.
Yeah. Okay.
Yeah. Hope team, we have seen this chapter a lot, very well.
I have one.
Please feel free to add your questions in the Slack so that it will get resolved. Also, I will share the feedback form. So please give suggestions to improve myself.
Since the question of math came up, the one thing I would mention is encourage everybody to look at the video on cross entropy that the same author has posted on YouTube. It's an excellent, very simple, but fundamental exposition of the cross entropy concept, and also it underlies all of what is attempted to be done in data science is finding the closest or most appropriate probability distributions and how they diverge and what are the metrics for the divergence, which all goes into the math. So I think if you have time and you need not be afraid of the math, because the math is very simple, he takes you through it, but I would strongly encourage people to look at that video on cross entropy.
Srinivas, can you please put the references in the Slack?
It's there in the book. It's there in the book. He has a link to the video in the book.
Okay.
So Srinivas, as you brought up the point of mathematics, actually I was going to ask something on that front as well. So in this chapter, we have seen quite a bit of mathematics, and even though that I think is a bit superficial. So can you tell me one practical example where learning all those maths actually pays off? So with today's
It begins, for example, it begins to go into what Anant asked. How do you improve your, and as we go into further details of the metrics and the laws, what kind of metrics would you devise and why is one metric better than the other? Or how would you change the functions, the underlying, and for example, in the cross entropy, there is the term Kullback-Leibler divergence. What does that mean as opposed to some other divergence for comparing the entropies of two values? So as you get into further details of what you would like to do, meaning your scores aren't improving, you might, when you're applying to a deep learning problem, for example, then you may want to use a different loss function. If you use a different loss function, you'll need to understand why is that loss function different, or how is it different, and why would it give you better or worse results for a particular problem. And while I still can't explain to you, for example, all the different divergences, it's good to be familiar with what is a divergence, what is it used for, and what are the probability distributions, and how do you compare probability distributions. Therefore, you can begin to understand the different loss functions and when you would use which one and why would you change from one to the other.
Okay, so you were telling that so we could do that using like different, using just the libraries, just calling the libraries and supplying the
yes, but exactly. But in order to even know what to use, which is more of an engineering stuff, you need to understand enough of the math. You don't need to be able to derive and prove what authors prove and derive, but you need to be able to understand enough to apply it. Otherwise, you'd just be randomly trying stuff.
Right. So what you're saying is that if we just randomly try that one, it will be like shooting in the blind.
Exactly.
Rather than,
whereas if you understand the loss, if you understand what is cross entropy, then you would know when to use that versus when to use something different, when to use a different kind of a loss, and why would a loss only approximate a metric instead of the difference between metrics and losses. And these things we learn more about in the book as well, but those are the reasons to get into at least having a base level, even if you cannot derive them yourself.
Understood. So Srinivas, can you suggest any book which goes into the depth of this? Not, as you say, whatever depth you find suitable, any suitable book for going into the maths?
Well, I mean, you could even just simply start with the recordings that Joseph posted of the I forget what Slack channel it is, but it's there in the Slack, and just go through and listen and go through the paper on, sorry, I don't, let me look at the.
Are you speaking of the matrix calculus?
Yeah,
Srinivas?
even matrix calculus stuff to look at, so you understand the basic math behind it. And there are other books that Joseph has posted previously and others have as well, which allude to the basic math of linear algebra, probability, and other things that you would need in order to become familiar with the math behind it.
Oh, thank you.
Yeah, so it's time to wrap up. So, thanks team, and thanks this community, and thanks Joseph and Srinivas. I'm not aware of an entire person's name. I'm sorry. So thanks all for this wonderful opportunity, for these wonderful discussions to grow us better.
Thanks, Rajesh. You've
Rajesh.
done a terrific job on Chapter 4, taking us all the way through safely and soundly.
Yeah,
thanks,
it's
Joseph.
tough mathematics, and good work by using the math world and Mathematica and so on to illustrate the concepts. I think
yeah, that was really excellent. Your use of Mathematica to produce those beautiful plots.
Yeah. So yeah, thanks all. So dropping the call now.
Okay, have a great day, everybody.